Hello, and welcome to our Slang workshop. In this lab session, Chris Habers and I are going to show you how to use Slang, the next generation shading language. This workshop was originally presented to a sold-out audience at SIGGRAPH 2025. In this version adapted from the internet, we'll get to go a bit deeper and include some bonus content that we had to cut for time in the live version. Since this lab is interactive, we'll have you write and compile Slang programs on your own computer and give you a few coding puzzles to solve. Through this, you'll learn how Slang can help you write fast, cross-platform shaders, and we'll even cover some advanced language features like modules and auto-differentiation. But you might find that if you know shading language like GLSL or HLSL, you can probably write Slang already. Here's an example of a shader that clears an image text frame to a solid color. Let's walk through it line by line, and you'll probably recognize the parts. First, we define a 2D texture named text frame. The RW stands for read and write, and we'll write RGBA colors to it using vectors of 4 floats. Thus, float 4. Then we define the shader entry point, which is a function. Above it, we have 2 attributes. The first attribute says it's a compute shader. And this attribute says the compute shader covers the image using threads in 2D blocks of 16 by 16. We won't get into the details of how compute shaders work, but for now all you need to know is that if the 3 numbers here multiplied together give you 128, 256, or 512, you'll get optimum performance. Our shader's input is the index of the thread in the compute shader dispatch. It's a vector of 2 unsigned integers, x and y. That's the pixel we're writing to. Then we define a variable called color, which is a vector of 4 floats. We set it to an RGBA color. And finally, we write it into the texture at the given pixel. If you've programmed shaders before, probably the only new thing here is this shader compute attribute. This allows you to define multiple shaders in a single file. The rest probably looks pretty familiar. In exchange for compiling this with Slang, you get a lot of features. Slang lets you compile your code for Vulkan, DirectX, OpenGL, Apple Metal, WebGPU, PyTorch, CUDA, Optics, and even C++ code, so you can run it on a GPU or CPU. And it lets you use the full capabilities of each target, avoiding the common denominator problem. For instance, WebGPU doesn't support ray tracing, but Slang will let you use it when you're targeting Vulkan, DirectX, or Metal. And it gives you advanced language features to solve the needs of today's graphics developers. It has shader reflection for getting info about shaders, auto-differentiation, which Chris will talk about. It helps you structure large codebases using modules, interfaces, and generics, as well as specialization to help with compile times. Types like pointers and parameter buffers that make shader I/O easier, properties for structs which even C++ doesn't have, and many more type features to help you write shaders. In sum, it's a shader language designed with 15 plus more years of wisdom in how to create languages for computer graphics. And its runtime shader performance can meet or beat handwritten code, even when using advanced features like generics. Slang is also open source and an open governance project under the Kronos group. Valve ported their Source 2 engine to it. Autodesk Aurora uses Slang to render on many different platforms, and Slang powers NVIDIA Omniverse and Portal with RTX. In this session, we'll get you coding shaders as quickly as possible with an interactive tool. Then we'll drop down to the command line to show you how to use the slangc compiler directly. If you're approaching Slang from GLSL, we'll talk about what's involved in porting your code to Slang. Passing data to and from shaders is an important topic, and one that Slang really innovates in. Then we'll go over debuggers and other tools and how they work with Slang. We'll get into some advanced language features in the Structs and Modules section. Then Chris will talk about SlangPy, which is really interesting for researchers, and finally one of Slang's standout features, its ability to automatically generate forwards and backwards derivatives of code. Let's get started! In the original version of this workshop, we had 60 or so computers in a room all running Linux. You, however, might be running on a different platform, and so we have multiple different ways that you can use the materials in this lab. If you're on Windows or Linux, the best way is to download the pre-built files that we have for you here. Just go to this link, download it, and then enter in the folder for your OS and run vk-slang-editor.exe. After you've downloaded that zip file, right-click on it and extract it. Once you've extracted the files, open the folder, and then you'll see multiple subfolders. Here we've included the slides, the SlangPy files, which Chris will use, and then 2 folders, one for if you're using Linux and the other for if you're using Windows. I'm currently using Windows, so we'll open up the Windows folder. Whichever folder you go to, double-click on vk-slang-editor.exe, start running it. And you should see a window that looks like this. Alternatively, if you're on an older version of Linux, or if that executable doesn't work for you for other reasons, you can build it from source. You'll need Git, CMake, and a C++20 compiler to compile it. To download and build the editor, open the command line. Then you'll want to go ahead and clone the VK-Slang editor repository, which should create a folder like this. CD into that directory. Then go ahead and make a build folder and CD into that. Now we'll run the CMake configuration step, the same way most projects do. And that will take care of downloading all of the necessary libraries and dependencies that are needed. Then run CMake, -- build, use dot from the current directory, -- config release, and then -- parallel, and press enter to start the build. This build process might work on Mac using Molten VK, but we haven't tested it on that platform yet. If you run into any issues during this build process, feel free to contact us via email or by making an issue on the VK-Slang editor repository. Once the build finishes, you'll find us in the _bin folder, under the release config, and then as VK-Slang editor. Double-click on that, and it should start up and run. Finally, if you only have access to a web browser, you can also use the online Slang Playground to get a taste for compiling Slang code. All you need to do is open your web browser and go to https://shader-slang.org/slang-playground. Slang Playground includes a number of examples. Note that some from the examples that we show off here will require some porting to the way Slang Playground works. In particular, whenever we say a main function, you'll instead want to implement things in the image main function. We'll talk more about Slang Playground later. Fantastic. Now, at this point, you should have Slang Editor open and displaying an example shader like this. If you need to, you can adjust the size of the text on screen by going to Editor and then using the UI Scale Up and UI Scale Down settings. You can also use Control and then mouse wheel to scale the UI up or down. Let's start with something really simple. Select the content from the main function in between the curly braces and delete it. Let's set all pixels to a solid red color. To do that, we'll take a look at our inputs. We have an RW texture2D float4 called text frame that we want to write to at the current thread. So go ahead and type in text frame, open square bracket, thread, which is a 2D index, and we'll set that to a float4 containing a totally red color. So float4 of the red channel would be 1.0, the green channel would be 0.0, blue channel will also be 0.0, and the alpha channel will be 1.0, although it can't be displayed on this monitor. Go ahead and click on compile, or press F3, and you should see a totally red screen. Similarly, if we change the color to something different, you'll see that color update. What we're doing is just for every pixel on the screen, since this function is called in parallel for all pixels, we're setting that corresponding pixel in this texture to this color. Now let's draw a gradient. For this, we'll take the x component of the thread index, which ranges from 0 to the screen width -1, and divide it by the screen width, which is contained in this I resolution uniform, to get a value between 0 and 1, which we'll put in the red channel, like that. Now, if we compile this, you'll see that I made a typo when I was typing I resolution. In this case, Slang will provide a diagnostics, which you can see in the window here, which will point to where the error is. If you run something like this, where you've misspelled the term, you can just put in the correct one, recompile, and you'll get a beautiful gradient. Now let's extend this to 2 dimensions. Let's create a float2 variable called UV, and set it to the thread, divide by the resolution. Slang will automatically convert the type. We'll then take the 2 components of UV and store them in the first 2 components of the float4. Compile again, and you should see red increasing as you go from left to right, and green increasing as you go from top to bottom. If you've programmed shaders before, you're probably feeling pretty comfortable at this point, and so the things we're going to cover next, like in-out variables and for loops, will already be old hat to you. In that case, you can go to Examples, SIGGRAPH 2025, and 1 Mandelbrot, and skip ahead a few minutes in the video. Otherwise, keep tuned as we build the rest of the shader. Now, with the rest of the shader, we'll build a Mandelbrot set effect. To do that, we'll want to create a function. It'll return a uint for the number of iterations. It'll be called Mandelbrot. And then as its input, we'll take a float2 coordinate, which we'll call z for mathematical reasons. For now, let's just make this do something that we can see on screen. Let's write an if statement. If the x component of z is less than, say, 0.5, i.e. halfway across the screen, then we'll make this function return 0. Otherwise, we'll make it return 1. And down in here, we'll want to call our Mandelbrot function with our UV coordinate and take its result and assign it to a uint called I. We'll take our resulting value I and just assign it to all three of the red, green, blue coordinates of our color. If you compile that, you should see that the screen goes from black to white halfway across the screen. This is not very interesting, so let's do something more interesting. Let's start by programming a step up to a Mandelbrot set called a Julia set. Go ahead and delete your if statement there. Now, for a Julia set, we'll repeat an iteration multiple times, and then if our point z gets large enough, we'll return the current number of iterations. So to do this, we'll use a for loop. We'll want to say for uint I, which will stand for our number of iterations, is 0. I less than some maximum number, let's go with 64 for right now. And then every iteration will increment I. We'll first do a task to see if z has become too large. For that, we'll say if the dot product of z and z, which is just in square length, is greater than some large number, let's choose 256. Then we'll return the current number of iterations. Otherwise, we need to do some math to z. This can be anything that you want, but the current approach is something called complex multiplication. The equation for that is z is equal to float2 of z.x times z.x minus z.y times z.y in the x component, and then from the y component, 2.0 times z.x times z.y. And then finally, we'll add some constants now to make it more interesting. Let's do negative 0.5 and 0.0. Finally, if we go through all of these iterations and we don't escape, then we want to return the maximum number of iterations there. Now, it's good practice usually when you have a magic number like this 64 to turn it into what's called a compile time constant. In Slang, compile time constants use the static const syntax. So here we'll create a compile time constant, which its type is uint, and its name is called kmax iterations. And we'll set that equal to 64. Then take each instance of this and plug it in there. Now, if you compile that, you'll get a totally white screen, because for most points, the number of iterations is greater than 1, and the brightest color that we can display on screen is 1.0. So for that, we'll take our number of iterations here and scale it down to a range we can see. For that, we'll create a new variable called color. Its type will be float3. It will just be I converted to float divided by the number of iterations. Then we'll take that color and place it into the first 3 components of that. And now you should see some interesting fractal curves. Let's go ahead and zoom out a bit. In this case, we'll want to set things up for the next step by setting UV equal to UV times 4.0 minus 2.0, showing off some vector math there. And there's our interesting fractal. Now for a full-on Mandelbrot set, we only need to change 2 lines. First off, we need to store the initial value of z in a float2 variable. We'll mark this as const, just to note that the value of this variable doesn't change. It's totally optional, but it makes your code more readable. Then we'll take that constant there and replace it with c. If you do that, you'll get a Mandelbrot set. Let's now spice up this color a bit. In the interior of the Mandelbrot set, we'll want the color to be completely black. So by default, let's make the color black. And then, if our number of iterations is not the maximum number of iterations, we'll choose some colors from a color palette. In this case, we'll set color is equal to a sine function of the number of iterations. If we do that, you'll see that now we have this repeating pattern. However, if we offset each of the channels inside the sine loop, 0, 0.5, and 1, then we'll get this multicolor effect because each of the red, green, and blue channels are reaching their peaks at different times. Some of these colors are too dark to appear on screen, so we'll just use the usual trick to bias nodes to a visible range. And then finally, let's make this coloring continuous. From that, it's a bit of a magic formula that we won't go into, but the equation for it is to take the log2 of the dot of the position that our point wound up. Now, our function only returns the number of iterations, so we'll want to return as well the new value of z. To do this, we'll take our function parameter here and mark it as in-out. That means that the value of z will be copied into the function from uv to z, and then at the end copied back out from z to uv. Now down here, our dot product can make use of our new position. Close that off with enough parentheses. If you compile that, you should see a beautiful smooth gradient. Now we can mess with this code to display some interesting things. Now, up at the top of the shader, you can see that this shader defines several shader parameters with the uniform qualifier. One of these is iTime, which is float, and then time in seconds since the shader started running. We've also got the resolution, which we already used, and iMouse, which is the current mouse position in pixels. Let's use iTime here to cycle the color palette. In our color palette function here, take our number of iterations, and just add iTime to that. Then recompile, and you should see a beautiful color cycling effect. Now I'd like you to try to modify the shader on your own. The goal of this exercise is to get you practice with Slang by making changes in the code, compiling, and seeing the result. So I'd like you to try breaking the shader, changing the control flow, modifying the equations, and experimentally seeing what you get. I put a few ideas up here. Try using the iTime or iMouse uniforms, or if you're feeling adventurous, try this third idea here. Try to be fearless with your changes and break things. It will autosave next to the executable before every compile, so you won't lose anything. And if things aren't compiling and you're stuck, you can reload the example. Go ahead and pause the video now and experiment, and then when you're ready to begin the next section, you can return back here. Welcome back. In this section, I'll show you how to use the lower-level slangc compiler. My goal here is to show you how to work with the bare metal in a sense. The tool you've been using doesn't do much beyond taking your shader, passing it to the Slang library to compile it to Vulkan's SPIR-V intermediate representation, and then rendering with it. Now we'll compile to targets other than Vulkan by using the Slang command line, slangc. First, return to your copy of VK Editor, and save your shader in the same folder as VK Editor, as example.slang. You'll see that we've already created an example Slang file for you, in case you had problems compiling during the previous section at all. Now go ahead and minimize VK Editor, and look at the folder again. You'll notice that we've included a copy of the slangc compiler in this folder. So we'll want to open up a command line in this folder. In Windows, the fastest way to do this is to click in the address bar and type in cmd.exe. This will pop up a command line in the current folder. In Linux, you can usually right-click in your window and select Open Terminal here, but this will depend upon your windowing system. Now, you should see the command line there. If you don't see your command line, you can, and if you're on Linux, you can type in ls and just make sure you're in the right one. Let's make sure slangc is working by printing out the current version. If you type in slangc-v, on Linux you'll need to preface all of these commands with a dot and a /. You should see a version number like 2025.13.1. If you're on Linux and you instead see a number that's about 1.7 billion, then don't worry too much. If you run into that situation, what probably happened is that you installed the Vulkan SDK at some point and added the Vulkan SDK to your LD library path. The Vulkan SDK also includes its own version of Slang. In that case, if you saw that 1.7 billion number, then that version of Slang got loaded instead of the local version. This is okay for the purposes of this workshop. The Vulkan SDK version will work perfectly fine. Now let's go ahead and compile that shader we just created to GLSL. For that, the command line is slangc example.slang, which is our file, and we'll say -target GLSL. Slang will output the result to std out by default, and you can see that this is a valid GLSL shader. It starts with the hashtag version pragma, sets some matrix layouts, which we'll talk more about later. You can see it has line directives to associate the source with the output. And then you can see, for instance, that our text 2D of float 4 has turned into a uniform image 2D, which is set to binding 1 and uses RGBA 32F layout. And similarly, our other parameters have been added to a structure, which is in a uniform block. And then our Mandelbrot function appears right here. There's our for loop, which has been transformed by the compiler into a different form. And then down here is our main function, again with line pragmas to associate the source and the output, but otherwise looking pretty similar to our original code. In fact, Slang does try to preserve readability. You'll notice that many of the variable names are in fact the same, and our global parameters are also the same. So it transforms the output as a compiler would, but also tries to keep the output readable. Let's take a look at some of Slang's other options. If we run slangc-h, Slang will print out a lot of info to stdout. Usually what I do here is I reroute it to a text file using slangc-h sign help.txt. If we now look no further, we'll see in this help.txt file, which includes all of our options. In our case, we're interested about the targets. What can Slang compile to? Go ahead and search for -target in this file. And you should find the list of targets that Slang can compile to here. There's quite a few of them. Let's go ahead and experiment with a few of them. SlangC, for instance, supports WGSL, the Web GPU shading language. In WGSL, attributes are often specified using @signs, and you can also see that bindings are specified in different ways. Additionally, texture 2D here has turned into a texture storage 2D. Similarly, types like vec2 now use bracket syntax, so it's quite a complicated transformation here. Slang also supports mehel. And mehel also has significant differences in syntax. Here, attributes are specified using double square brackets. Global parameters are passed in as inputs to entry point functions. Here's our render entry point, and assigned to different binding indices. The one that VK Slang Editor uses, because it's based on Vulkan, is SPIR-V. And if you do that, you'll notice that Slang outputs the disassembled version of SPIR-V, if you're familiar with it. SPIR-V has both ASCII and binary forms, and usually what we want is the binary form. So to get that, we'll want to write it out to a file, because most consoles can't display binary output. So for that, we'll append on the -o argument, and then give it a file name. Let's call it example.spv. If we do that, then you'll see that we now have file in that folder. If we open that with the hex editor, you can see that it has the binary format that a SPIR-V file would. As you might have noticed, some of the outputs are very different than their inputs. Some studios use preprocessor-based systems to support multiple platforms, but for things like SPIR-V or WGSL, you really do need a full compiler with its parsing and codegen systems. As a compiler, Slang works by taking the input and transforming it to an intermediate representation called SlangIR. All its optimization and other passes operate on that IR, and then it outputs code for each target below. For some targets, like DXIL, it'll output HLSL and then call a downstream compiler like DirectX Shader Compiler. Now let's talk about the specifics of some targets you may have seen. Earlier in our GLSL example, Slang in fact renamed the entry point, which was called render, to main. This is because OpenGL only allows you to have one entry point, which must be named main, since GLSL doesn't have ways to mark functions as entry points. So if a Slang file contains multiple entry points, you have to select one at a time using the -entry argument. Vulkan and SPIR-V, on the other hand, allow you to have multiple entry points. So for that, I recommend using the -fvk-use-entry point-name argument to keep the original entry point names in the output. Slang also has features for taking GLSL-like code as input. Suppose you're a developer with, say, tens of thousands of lines of GLSL code, and you'd like to make use of some of Slang's features, like reflection. The good news is, Slang can compile GLSL shaders with almost no modification. You only have to do a few things. First off, make sure your shader uses the GLSL #version directive somewhere. This tells Slang to load in its GLSL compatibility module. Then you need to mark your entry points with shader attributes to tell Slang which functions are entry points for which shader types. Most attributes are handled automatically, but if you're porting a domain, whole, or mesh shader, which is less common, you have to translate those specific GLSL attributes to HLSL equivalents. It's usually straightforward. And then you're done. That's all you have to do. You're all shown this process in action by porting a shader live. Here I have a shader I wrote about a decade ago. This is totally valid GLSL. You can see our version pragma, and you can see our main entry point there, as well as GLSL style layouts and bindings. If you gave this to a GLSL compiler, it would be valid. For now, I'm just going to take this and copy and paste it into VK Slang Editor as if this were already a Slang shader. If I go ahead and naively compile it, you'll notice now I get an error about an invalid SPIR-V magic number, and that's because I haven't defined any entry points. I've got a main function here, but I haven't told Slang that this is an entry point. So for that, I'll need my shader compute attribute, just like we had in the start. Go ahead and compile, and that's it. That's all we need to do to get this compiling. Now, if you're used to GLSL or HLSL, there is one thing that you might be worried about. GLSL and HLSL typically have opposite matrix layouts and conventions from the order in which you multiply vectors and matrices. In GLSL, matrices are column major and matrices usually appear on the left. But in HLSL, matrices are row major and matrices usually appear on the right. The good news is that Slang's GLSL compatibility layer automatically handles this transposition for you. It'll translate GLSL style M star V to HLSL mul of V and M. This can be a bit of a brain twister. My team at work was involved in porting several code bases from GLSL to Slang and went back and forth on different approaches. Based on that, we have a recommendation. Specify row major layout and then don't mess with your code. Because Slang's GLSL compatibility layer swaps the order for you, row major CPU matrices will show up as row major HLSL matrices and as column major GLSL matrices, which is correct in both APIs. So if your GLSL matrix math was working before, it'll work now. If you're using the GLM or DirectX math libraries, you can memcopy the matrices to memory. There's no need for transposition. And row major CPU matrices are natural to view in the debugger and have slightly better access patterns from the GPU. So basically, specify row major and then don't touch your code. The second most important thing is to always specify the matrix layout in the compiler flags. Slang's biggest pitfall at the moment, in my opinion, is that the library and the executable compilers default to different layouts. The Slang team is hoping to make these both default to row major in the future, but for now it's best to always specify it. Finally, earlier when we compiled to GLSL, you may have noticed that GLSL listed a row major attribute, even though in the command line it defaulted to column major. This is because of that swap I mentioned in the last slide. The GLSL and SPIR-V layout will appear as the opposite of the Slang layout. Don't worry though, CPU row major / SPIR-V column major is still the better access pattern. This connects to a larger topic, shader input and output. Most shaders operate on data in some way. For instance, a fragment shader might load material properties from one buffer, sample textures, and finally output a color to a frame buffer. Typically, the way this works is resources like buffers and textures exist in video RAM somewhere, and app writes descriptors, which are like pointers with some extra info, into descriptor sets or descriptor heaps, and then binds these descriptor sets or heaps in the rendering pipeline. The part we'll be talking about today is how we can write Slang code that accesses resources. There are many kinds of resources, and each one has a type. For instance, here we define a texture 2D called text. That'll bind to a 2D texture object. Calling texture2d.load loads the value of a single texel. Texture 2D objects are read-only. To read and write to them, we need an RW texture 2D, like we saw in the intro example. You can also have 1D textures, 3D textures, and cube map textures, as well as more complex texture types like arrays, multi-sample textures, feedback textures, and more. Now, textures by themselves only give us point filtering. In order to get linear filtering, we need a sampler state object. That'll bind to a descriptor, saying what kind of filtering to use and how to interpolate between MIPs, as well as what to do if we sample outside the texture. In Slang, we can write code like this more concisely by using the new sampler2d type, which is a texture 2D plus a sampler state. To sample it, we just call sample. In Vulkan, this maps to a combined texture sampler, which is a single descriptor, while in DirectX, this maps to a texture and a sampler. You can also have linear buffers of data. Byte address buffer is a raw buffer of bytes. Like RW texture 2D, there's an RW byte address buffer type that allows both reading and writing. A structured buffer is an array of a given type. For instance, here we define a material struct and then the buffer of materials. Slang also has constant buffers, for read-only data limited to a maximum of usually 65,536 bytes. Constant buffers can be faster than storage buffers, especially when all threads in the wave read the same element at the same time, but it depends upon how hardware implements them. In our earlier Mandelbrot example, when you were reading uniform global constants like itime, you were actually reading from a constant buffer. Slang places global uniforms like these in a global constant buffer for you. Vulkan push constants, also known as root constants in DirectX, are even better than constant buffers when you have a small amount of data that changes every call. They're limited to 128 to 256 bytes usually, but they're good for things like IDs and model transform matrices. In GLSL, the syntax for push constants is kind of strange. You define a constant buffer, and then when you're creating your constant buffer, you have to say, actually, this constant buffer isn't a constant buffer, it's a root constant. If you're targeting SPIR-V, you have to add this vk push constant attribute. Slang supports that, but also provides cleaner syntax. If you mark an entry point parameter as uniform, then in SPIR-V, it'll translate to a push constant, and for DirectX, it'll show up as a root constant in reflection info, which we'll talk about in a few slides. Graphics techniques often require multiple uniforms and resources. On the left, we have in the fields for a fairly typical environment technique. We've got a sun, direction, and color. Then the fields for a cascaded sun shadow map. For texture layers, the transformation matrix for each layer, and a sampler that does comparisons for percentage closer filtering. And finally, a Q map for the sky dome. In traditional shading languages, we can't group these together. Because you can't have textures inside constant buffers, we're forced to separate uniforms into a struct and put them into a constant buffer. Because of this, these might be dozens of lines apart, or even in different files. We have to make sure their variable names don't conflict with other things in our codebase, and it gets messy. Wouldn't it be cleaner if these were in a single struct? Like, don't these want to be in a struct together? You can now do this with Slang's parameter block type. Now we can place all of our environment parameters in the struct and place that in the parameter block. When compiled, Slang will do the work of separating these into descriptors and constant buffers. While we're writing it, they're nicely visually grouped together. We can even treat parameter blocks like other types. So for instance, we can place them in structs or even nest them. So far, we've been talking about resource types. The second part of shader I/O is defining where the shader expects the descriptor for each resource to be. If you want to explicitly specify this, there are three main ways. DirectX uses different indices for textures, constant buffers, UAVs, which are larger buffers, and samplers. So in HLSL style, we can say that the color texture is bound to texture index 3 and space 0. Vulkan is a bit simpler. It uses one index for the binding and one for the set. HLSL and GLSL have different ways of specifying this. The good news is that you can choose whichever one of these is your favorite. Slang supports all three. When a shader needs a lot of resources, so for instance a ray tracing shader that needs access to every vertex buffer in the entire scene, using a separate binding for every resource is just impossible, or can just be a lot of bindings set, which slows things down. The solution to this is to bind less. Instead of having a binding for each resource, we have an arbitrarily sized buffer of descriptors somewhere in memory, and then we point to that and say, go read from resource number 5, for example. Previously, one problem was that Vulkan and DirectX phrase bindless in different ways, and they use raw indices, which loses type safety. Slang introduces the descriptor handle type, which converts to whichever bindless representation your API uses. So in the code here, we say that binding 0 and set 0 is a buffer of descriptor handles for texture2D objects, and we do a similar thing for vertex buffers. You can use descriptor handles like the objects they point to. The only thing you need to make sure of is, if you can have different threads in the same wave accessing different resources, then you need to tell Slang by wrapping the handle in the non-uniform qualifier just before you use it. Finally, if you're compiling to targets like SPIR-V, C++, and CUDA that support them, Slang will let you use pointers. This makes writing some data structures a lot easier. So for instance, here we're defining a linked list, just as easily as if we were writing CPU code, except this can run on the GPU. Finally, the app and the shader have to agree on the binding indices and types somehow, so that the app knows how to set up rendering pipelines and update uniform buffers correctly. This is a fairly common problem. The usual solution is to add a third file that defines all the binding indices and constant buffer structures, and then to include this in both the shader and the app. Since it's included by both Slang and C++ code in this case, it must be a polyglot, readable by both languages. And if you're familiar with layout rules in GLSL, you might notice that we have to be really careful about the alignment on the float2 field after this float3 field, or that we have to use scalar layouts, which are my preferred solution. That said, this tends to work pretty well. With Slang, another option is to use shader reflection. When you compile a shader with Slang, you can also get a Slang program layout object that tells you every shader parameter's type, contents, and binding. Then you can use that to automatically generate your bindings on the app side. And on the shader side, your parameters look a lot simpler, since you don't have to explicitly specify binding indices anymore. Reflection information includes resource types and binding indices, but also includes a lot more. You can get how structs are laid out in memory, and the names of each in their fields, each from the entry points in their attributes, and much more. In fact, this is how the editor you've been using works. Whenever you compile a shader, it looks at the reflection info to figure out how to set up its pipelines and how to update its constant buffers. So for instance, if you added a parameter named I in a previous exercise, VK-Slang editor would look at the shader inputs, see that there was one named I, and would go, ah, that's asking for the camera position. I should add camera widget and start updating that uniform with the camera position. Here's an example of a compute shader where we implement 3D perspective using this I parameter. Slang Playground, which is an online Slang editor, uses a similar solution, except it uses custom attributes instead of looking at variable names. For instance, this playground : time attribute is a custom attribute. That's defined in the playground module, and we'll talk more about modules later. The one downside of reflection is that if you're using it to update uniform buffers, the additional lookups required will probably make it slower than the common header solution, unless you generate assembly on the fly. Reflection is a big topic in and of itself. If you're interested in learning more, I highly recommend checking out Testfully's online talk about it. For my next activity, I have a bit of a puzzle for you. In VK-Slang editor, go to Examples, SIGGRAPH 2025, and then to Shader.io. You'll have a shader net loaded in here, but you'll notice that some of the types are missing. Your challenge is to figure out the missing types, using the comments as your guide. I've already filled in one of the comments for you. So for instance, this readable and writable buffer of particles should use an RW structured buffer type. Go ahead and pause the video here and see if you can figure out the missing types. Once you think you've gotten them, press compile. If you see any new diagnostics, that will give you hints on how to solve the other ones. But if there's no errors in the diagnostics window, you've solved it correctly, and you should see a neat shader show up here. Go ahead and pause the video now, and then when you unpause it, I'll go ahead and present the solution. Alright, welcome back. Let's take a look at the solutions in this puzzle. For this, for k-num particles, which should be a shader parameters use the uniform qualifier. And since this is type uint, our syntax there is uniform uint k-num particles. For the next one, we need a readable and writable buffer of uints. This was readable and writable buffer of particles, so we just do a similar thing here. It's RW structured buffer of uint, and then close it off. For a 2D readable and writable texture, our type is RW texture 2D. You may notice that we don't need to actually specify the type here. I'll talk about that more later in the generic section. And finally, we need a 2D combined texture and sampler. This is probably one of the trickier ones because the combined one is not named after the texture, it's named after the sampler. The corresponding type is sampler 2D. If you go ahead and compile that, you'll have solved the puzzle. Fantastic. Let's go on to the next section. Now let's talk about tooling. Slang has a wide amount of support in IDEs and debuggers. If you're using Visual Studio or Visual Studio Code, Slang provides official language extensions. In addition, any editor that supports a language server protocol, which powers things like syntax highlighting, IntelliSense, jump to function diagnostics, and much more for languages such as Python and Rust, can also use Slang's language server, slangd. For instance, this is how auto-completion and function definitions work in the editor you've been using in this lab. Debugging Slang shaders also works like debugging other shading languages, so you get a pretty natural experience. To give an example of this, I'll go ahead and debug a shader live. Here I've opened RenderDoc and filled in the executable for a fairly simple 3D rendering example set up by my colleague, Martin-Carl Lefrancois. If I go ahead and launch this with RenderDoc attached, you'll see that we have our polygons here, our polyhedra here, and then the RenderDoc capture overlay up there. Let's go ahead and capture frame using the F12 key, and then close the window. RenderDoc will automatically load in capture, and we can go through and watch as the frame is rendered. Let's go ahead and look at how this torus is rendered. If we go ahead and look at the pipeline state, we can see the vertex shader, the fragment shader, and each of the different input stages. So here, for instance, you can see that RenderDoc has loaded in the metadata from the Slang shader, and identify the position and the normal. We can even go into the mesh view and visualize our mesh, and see that Slang also provides these names as the input position, input normal, and then the output system value position attribute, and the different position and normal attributes to our entry point parameters. We can also take a look and debug the shaders directly. If I click on Vertex Shader, you can see our different bindings. So here we have a uniform buffer bound to set 0, slot 0, and we have a push constant there. If we inspect them, you can even see that the names of each of the different fields and their types have made it into the RenderDoc. So here, for instance, data, the data of proj for projection and view are both 4x4 matrices. And since we're using row matrix layout, these matrices are exactly as how we would imagine them. We also have our camera position there. We can do similar things for the push constants, which include the world of view matrix. If we go back to our mesh view and select a vertex, we can even debug the shader, or run RenderDoc's emulation of shader debugging. So if we go over here, right-click on a vertex and say debug the vertex, you'll see that RenderDoc can load in the shader, and we can even step through it. Here our position as a float 4 is equal to this. And we can even look at our output structure as it's constructed. So it works pretty much as you would expect. Now, to make your app easier to debug, the most important thing you can do is to specify -G1 on the Slang command line. This will make formats like SPIR-V embed a copy of your shader code, so even if the debugger doesn't have shader search path set up, it can still load the shader source. This is what RenderDoc is relying upon here. Slang will also automatically generate line info, mapping from output instructions to input lines by default. When releasing your app, you might want to do the opposite. You might want to make your shaders harder to debug. Slang gives you a few options here. You can remove debug info by setting -line-directive-mode to none. Or you can split off the debug info into a source map or into a separate SPIR-V file. Then you get the best of both worlds. For release builds, you can debug your own code as long as you have the source map, but in release, if you don't provide the source map, it's much harder to reverse engineer. Now let's talk about some of Slang's advanced language features, which make writing everyday code easier. Structs are all about organizing variables. For most of my examples, I'll use a struct that looks like this. It contains a float, and the pointer is some unsigned integer data in memory. The first thing you might notice is there's no semicolon after the struct. This is purely a convenience feature. You don't have to have them in Slang. Usually when you have a type like this, you always want to initialize it with some default values after you create it. HLSL and GLSL don't have constructors, so usually you have to initialize fields explicitly or do so on their workaround. Slang lets you define constructors for types now. Constructors are functions named __ init with 2 underscores. This is a default constructor that is called whenever you create a struct of this type. You can also provide parameters to constructors like this. Or you can have default values for struct members and Slang will auto-generate the constructor. Structs can also have functions. These work like member functions in other programming languages. And you can have static member functions. Here id is a static function and I can write sdf info : id. Functions are const by default. If a function changes struct values, then you need to mark it as mutating. Slang also lets you make member variables and functions private using the private keyword. This is useful for the same reasons as in C++ and other languages. You can also overload operators for structs in Slang. Earlier in our Mandelbrot example, we had some math on float2s that was really doing multiplication for complex numbers. But a cleaner way might have been, instead of using float2s, define a complex number type, and then make it so that the multiplication operator does complex instead of element-wise multiplication. Then our Mandelbrot iteration would have been a lot simpler. Structs help organize code on a small scale. Now let's talk about organizing larger code bases. Slang lets you include other files, like other languages do, but this old technique has some downsides. Since hashtag include works by virtually substituting in the text of files to include and then compiling the results, if a single header changes, then everything that depends upon it has to be recompiled from scratch. HLSL and GLSL also don't let you have private functions in headers. And there are smaller issues. For instance, preprocessor defines can leak out of the file they were defined in. With Slang, there's something better. Slang introduces support for modules in shader languages. These look a lot like standard include files, but they're compiled separately and then linked together. This can improve compile times, as we'll talk about in a bit. You can also have public, private, and internal members. Private members are only visible within the current file, while internal members are visible to the rest of the module if you have multiple files making up a module. And things like preprocessor macros don't affect other files. I should also mention that you don't need to specify internal on the SQR here if you use Slang language version 2025 or newer. That is, if you specify -lang lang 2025 on the command line. Notably, Slang's standard library uses modules. All Slang files link with HLSL.method.slang. And when you enable GLSL compatibility by adding hashtag version 460 at the top of your file, Slang links with GLSL.method.slang as well, which provides things like the star operator for matrix vector multiplication. If you're ever wondering how Slang's intrinsic functions work, you can look at their implementations. Reading these files is also useful for learning about advanced features like inline assembly, which lets you use features even Slang doesn't know about yet. Now, a quick word on compile times. Modules can help with compile times if you use them more than once. Here's a diagram of an app compiling 8 graphics pipelines. The input for each one is a shader that links against a larger library. Slang compiles shaders to SlangIR and links them together and emits target code, like SpearV. When the app creates a pipeline at runtime using a SpearV module, the graphics driver will usually do its own set of optimizations, producing GPU assembly. If you use modules, you only have to compile the shared library once, and then you can link each shader against it, saving time. In practice, for a hot reload benchmark I put together for a path tracer, I saw this reducing compile times by about 30%. Another thing that can help is specialization constants, like in Vulkan, which are designed to reduce shader combinations. Instead of, say, compiling different shaders for 1 light, 2 lights, or 3 lights per pixel, you can use a variable at the Slang level and only specify its value when the driver needs to do final optimizations. New in Slang, you can also do link time specialization, where you can specify types for things after compiling but before linking. All of these taken together reduce the total amount of work quite significantly, but you can see we're still paying the load time cost from the driver to optimize and generate GPU assembly for each of these pipelines. So we're not quite in an ideal world for shader compilation yet, but we're moving towards there. Finally, let's talk about interfaces. It's pretty common in computer graphics to have multiple objects that all conform to some sort of higher level interface. For instance, point lights, directional lights, and spotlights are all kinds of lights. Mirror, Lambert, and GTX are all BRDFs, and so on. If we want to have one struct for a point light and another for a directional light, if we want to sum over all point lights, we can write a function to do that. And if we want sum over all directional lights, we can also write a function to do that. And the code inside these functions will look exactly the same. So ideally, we'd like to generalize this function somehow. Slang provides a solution to this. First, we define the interface in the box on the top right. This is saying that any type that conforms to the iLight interface must have a function called irradiance that takes in the float 3 position and returns a float 3. Then, over on the left, we say that point light implements the iLight interface by adding a colon followed by iLight, and we do the same thing for a directional light. Now we can write a function called lightSum that can take in any light type. This is a generic function, and in fact, we've been seeing generics this whole time. TextureDD and structured buffer were generic types, for instance. Generics are a lot like C++ templates. Really, the only difference is we need to say what interfaces or types conform to, and this works really well with modules. In C++, for instance, you usually have to put all your templates in these massive headers so that compilers can look at their definitions. With generics, these can be in separate modules. No need for headers. On the left, the compiler only needs to check that point and directional light conform to iLight. And on the right, it only needs to check that lightSum uses only what iLight gives it. And you also get better compile time errors as a result. No super long compile errors about something failing in the internals of SC unordered map, for instance, when you just forgot to provide a hash. Let's put this into practice with my final puzzle from this lab. In VK Slang Editor, if you load examples, SIGGRAPH 2025, 3 interfaces, you'll see a path trace scene with several colored boxes, all using a diffuse BRDF. Now, this seemingly random arrangement of boxes, in fact, conceals a hidden image. Your challenge is to reveal this hidden image by turning the cyan plane here into a mirror. To do this, you'll need to remove line 14, and then write a struct called mirrorBRDF that conforms to the iBRDF interface and reflects the input direction along the hit normal. The struct that you'll define will start with struct mirrorBRDF, iBRDF, i.e. implements the iBRDF interface, and then you'll have to figure out what to put inside mass. Go ahead and pause the video here, and once you think you've gotten the answer, go ahead and press the compile button to see if you have reflection working properly. Once you unpause the video, I'll show how to solve this puzzle, and then Chris will cover SlangPy and auto-differentiation. Good luck! Welcome back. I'm here to present the solution to this puzzle. Our mirror_BRDF function needs to implement this iBRDF interface, which you can see below. Anything that implements iBRDF has to implement the static float3 sample function, which takes as input this hit info structure, and an RNG, which is unused, as we mentioned in the comments here. So let's go ahead and add in the function prototype there. And now we need to implement this. Now, our hit info gives us a direction and a normal, and we need to reflect the input direction look across normal. So for that, we'll use the reflect function. We'll say return reflect of hit.direction across hit.normal. And that with the semicolon, compile, and you should see a reflection. In a few seconds, you can see that the hidden image is in fact a check mark, telling you that you've solved the puzzle. Here are 2 more fun tidbits that we didn't have time to talk about in the live version of this lab. In Slang, you can also add properties to classes, which look like member variables, but are in fact a getter and a setter function. So here, for instance, I have a struct that holds a linear RGB color, but in some cases, it's just more convenient for me to give it sRGB colors. If I wanted to add a way to automatically convert sRGB colors, I'd usually have to add a getSRGB function and a setSRGB function. Here I'm doing this instead with a property, which lets me write this really concise code on the right. On the right, for instance, we're just assigning to the sRGB property and reading back the linear property. The sRGB property is in fact a pair of get and set functions. The get function returns a value, and the set function takes a new value, which is the input of NAS. Slang also has extensions in this to let you name the inputs in the set function something other than the new value. Finally, a neat thing is that you can tack on interfaces to structs after the fact. So imagine you're writing code that depends upon 2 external libraries. One defines an SDF info struct, but doesn't implement any interfaces for it. And another defines a min function that works for types that implement iComparable, which is Slang's built-in interface for types you can use less than, equals, and greater than operators on. If you want to use the SDF info struct from library 1 with min from library 2, normally in C++ you'd be out of luck and you'd have to modify library 1, or you'd have to implement another copy of your min function that is specifically generalized like SDF info objects. But in Slang, you can add on an iComparable implementation after the fact to SDF info, just like this. Now SDF info works with this min type, and you didn't have to modify either library. For the rest of this lab session, I'll turn it over to my colleague, Chris Hebert, who will talk about SlangPy, the Python version of Slang which is extremely useful for researchers, and finally auto-differentiation, one of the new features in Slang that changes in the game. Please welcome Chris Hebert.
Thanks to Nir for that fantastic Slang presentation. Now let's talk about SlangPy. What is SlangPy? It is a method of calling Slang shaders directly from Python. I mean, it doesn't get better than that, right? So this workshop, we're going to be using SlangPy, which is a Python library. We are also going to be using VS Code and IPython notebooks. So a quick word on dependencies and installation. Very easy to install. You really just go pip install SlangPy. So if you're a Python head, you'll know how to do that. Worth setting up a Python environment to work in. So if you're new to Python, it's very simple to do. You can use the Python VM package if you're working on Linux. You can also use Conda. But the setup for SlangPy is incredibly simple. You can also pull the latest SlangPy from GitHub and build that directly as well. So a quick word about IPython notebooks. So running these in VS Code is very, very simple. And again, if you're not familiar with IPython notebooks, it's simply a collection of code cells and a collection of markdown cells. So this allows you to experiment with little snippets of Python code and iterate and test and display the output very, very easily. It's a really great, great tool. So they implement seamlessly within VS Code. They can also run in a web browser. So in order to run a code cell, and we'll just look at this very quickly. You would place your cursor in the cell itself, and then you can just click this little play button, and then that is going to execute that cell. You'll see if it executes successfully, you'll get a little green tick there. If there's an error, you'll see errors down here. If at any point during this session you get stuck or you get left behind because you're experimenting and playing, which is exactly what you should be doing, one thing you can do is you can click for example, the restart button will just restart everything. Apologies for the big beep there. And then go run all, and then that'll just run everything. But ideally what you want to do is to go through this workshop cell by cell and then click each one as we go. So I'm going to clear all the outputs to get us back to where we were. And I'm going to go back to our slide deck. So we're going to look at the Mandelbrot set. So this is from Nia's session, and it's a really great, I love the Mandelbrot because it gives you the ability to really test out a language or environment, gets nice visual feedback in very, very few lines of code. So back to our Python notebook. Incidentally, there's lots of notes here that you can read through, and this gives you the information on how to install and everything else. So pretty much everything that I walk you through in this workshop is going to be documented in the Python notebooks themselves. So you can wander through at your leisure. So the first thing we're going to do is just what we did a few moments ago. We're going to put our cursor into our first cell, and we're going to import SlangPy as SPY, OS, NumPy, Matplotlib, and PyImage, which is an image processing library. We also have IPython display, which gives us some display capabilities within this notebook itself. So clicking on that little play button gives us a little green tick. We know we're good to go. So the first thing we're going to do in order to display that shader, and incidentally, the shader is here, and it's exactly the same shader that Nia showed in her session. So back to here, the first thing we do is we'll create a SlangPy device. So by going device equals SPY create device, we specify the include paths, and the include paths in our case is our current working directory, and that just tells SlangPy where to find the Slang shaders. Because with SlangPy, we're literally running the same shaders that we'd run if we're using Slang in anything else. We're going to create a texture. We're going to specify the width and height, 1024 by 1024. We're going to specify the format of RGB A32 float, and we're going to specify its usage similarly to how you would do that in Vulkan or DX12 or anything like that. So let's execute that one. And there's a little green tick, so we know we're good to go. So the next thing we'll do is we're going to load the shader that we saw. For this, we're going to call SPY module load from file and then pass in the file name. We then go .render. Now in the Mandelbrot set, we have a method called .render. So by calling .render, we are literally calling that method within that module. And then we go set text frame, iTime, iResolution, and mouse. And what we're doing here is we're just setting these global bindings here, these sort of uniforms and textures we can do with that call to set. So we're not setting up descriptive tables. We're not staging memory or anything like that. We're just going to call set, and there it goes. Then we call dispatch, and that will literally dispatch this compute kernel. We're passing in the text width and the text height to specify the launch bounds. And then the last thing we'll do is we're going to call display, and display is basically going to display this with pillow. And there it is. There it is. So if we look at that, that's all we did. We created the device, we created the texture, we loaded the module, and we displayed it. Now that's 4 lines of code. That's initialize, allocate, dispatch, display. 4 lines of code. Now, if you're used to working with Vulkan, you'll know that to do that is going to be several hundred at least lines of code in order to do that. And don't get me started on DX12. So let's talk about what SlangPy actually is. So SlangPy, it's a very simple path to working with Slang. So as we said, there's no need to wrestle with thousands of lines of C++ code to test a 100-line shader. You can dispatch a Slang shader with as little as 3 lines of code. Means you can iterate on prototypes really, really quickly. You can play around with ideas really, really quickly. There's also another important aspect, which is it helps us bridge the gap between graphics and machine learning. So SlangPy has a number of features which facilitate machine learning capabilities, such as auto-differentiation, which we'll look at in a moment. So you can also use SlangPy along Python's massive ecosystem of libraries. You've got the obvious, the usual suspects such as NumPy, Matplotlib, Pillow, and there's hundreds, thousands of others that that you can use and integrate seamlessly with your day-to-day usage of Slang. You can also design and test new operators for something like PyTorch, which has a Slang backend. It also abstracts away the details of working with threads, but it's still there if you want it. So if you're used to working with compute in CUDA or Vulkan or DX, then you'll know that if you're looking at a compute problem, depending on the type of problem, you're usually going to want to decompose that into a massively parallel set of work, which you would then dispatch across a bunch of SMs on a GPU. So SlangPy does allow you to do that, but it can also abstract it away if your problem is simple or not performance critical. And to be fair, even for some performance critical problems, SlangPy does a fantastic job of working out what the best way to dispatch that is going to be. It supports a large variety of backends for most platforms. I think almost all platforms, in fact. So I think Vulkan is one of the main ones. So when you create your SlangPy device, as we saw earlier, it's going to it's going to use a default device from its RHI, its rendering hardware interface, which is usually Vulkan. But you can specify others. You can specify DirectX if it's there. You can also specify WebGPU and CUDA. If you're on the Mac, you'll be using Metal. In fact, I think it'll just default to Metal on the Mac. So I think I want to say a little bit more about the sort of bridging of this gap between machine learning and graphics. So traditionally, we've had things like PyTorch for machine learning. We've got NVIDIA CUDA. We have Python, TensorFlow. And then on the graphics side, we've obviously got Vulkan, DirectX, WebGPU. Slang and SlangPy are kind of a common link between the two. So by using Slang and SlangPy together, you can very, very easily target a machine learning environment or a graphics environment. And as is becoming increasingly common, you can put the two together. And we'll talk more about this when we come to auto-differentiation in a moment. So I want to go back to our notebooks and show you a few more aspects of Slang and SlangPy in its simplest form. What I want to look at now is a very, very simple problem. We're going to draw a quadratic curve, which is almost the simplest thing you can do with anything. So what we're going to do is we're going to generate a series of points along the x-axis, and then we're going to run a kernel, which is going to compute the y based on the quadratic function. Now, we are going to be using the SlangPy intro slang kernels for this. We have a number of very simple functions. There's a few versions of quadratic. We have a simple quadratic, which just receives three floating point coefficients and then an exposition. We have a version which will take a struct, and then we'll have a final version which will take a struct as input and output. I want to draw your attention to this differentiable version. We'll look at this in part 2. So going back to the SlangPy intro Python notebook, let's do what we did before. We're going to create a SlangPy device, and we're going to load a module. We're going to load that module that I've just shown you. So by doing that, we get our little green tick, so we know that that's loaded successfully. So now we're going to generate some input data using NumPy. So this is where we're going to generate some points along the x-axis. We're just going to specify 120 points, give it a value of -10 to 10. Specify some coefficients. I've hard-coded those rather than using random ones. And then we can call our cubic function from SlangPy. Now, we're going to specify the output as a tensor. And we're going to call module quadratic. So just like we did with the Mandelbrot, we have our quadratic method in there, and we can call that directly from the model once that's loaded. In this particular case, we're going to pass in our arguments directly because these arguments here are going to match up directly with the function signature that we're actually calling here, which is our x inputs and our 3 coefficients. So if we run that, we get a little green tick. So that will have executed that quadratic function on all of these x input points here. Now, when we come to plot the results, notice that we have our output is an XPY tensor, but that's a NumPy-like object. So we can pass that directly to Matplotlib to plot that. And there it is. So we've gone from Python to Slang, back to Python, and then plotted that the same as we would plot anything else in Python incredibly quickly, just with a few lines of code. So with our SlangPy intro quadratic function, as we said before, we passed our arguments in as 4 floats. Now, obviously, A, B, and C, these are quadratic coefficients. They're just scalar values. But X was obviously an array. So we passed in an array of 120 odd X inputs. So SlangPy has seen this, and SlangPy understands and knows what you want to do with that. So it understands that it's going to pass these as scalar values, probably as push constants, and it knows that this is going to be a buffer of some kind, which it's going to translate into threads. So SlangPy has got your back, and it will deal with that for you. But so if we wanted to pass our arguments as a struct rather than raw floating point values, we can do that as well. So looking back at SlangPy intro.slang, I'll define this struct of quadratic coefficients. We've got an A and a B and a C. And we got version 2 of our quadratic function, which takes our floating point x, which SlangPy will translate into an array of floating point x's and then call this that many times, and passes in our quadratic coefficient struct instead. Now, this is where we can look at how we would deal with reflection using Slang and SlangPy together. So as you saw, we have defined our quadratic coefficients in our Slang shader, which means that we can get that type and give that to Python by calling module.quadratic coefficients. And then when we create our quadratic coefficients variable in Python, we can specify that as the type. And then we can just populate that like we populate any other dictionary object in Python. Let's do that and then print our coefficients, and there it is. So we can pass that directly to our module v2. Again, we're using a tensor, and we're going to plot the results just like we did before. And there we have it. So what about buffers? So can we create a buffer of types declared in Slang and pass that directly from Python? Yes, we can. So looking back at the SlangPy intro.slang, we have got our version 3, which we got a structure for quadratic input, and we got a structure for quadratic output. And what we're going to do here is we're going to create 2 buffers. We're going to use the SPY ND buffer, which is one method of creating a buffer in SlangPy. And what this is going to do is it's going to create the resources on the GPU and the CPU and allow you to transfer your CPU data onto the GPU. It's basically abstracting away the whole process of staging memory. So we create our buffers, both input and output, in the same way. Again, we're going to use reflection to get the data type from our Slang module that we looked at earlier, and we specify the shape like we would do like a NumPy ND array. Let's execute that, and there it is. Now we can look at this thing called a cursor. So our ND buffers give you an object called a cursor, which is like a doorway into that buffer. So what you can do is you can go through your X points that we created, and then we could write a value from those X points directly to each element in that buffer. Now, in this particular case, we actually have a buffer of 4 values. So we actually have an array of 4 values. So this is maybe slightly less efficient than doing it with the floating point versions if we're passing everything as a buffer like that. But there may be cases where that would make sense. When we call cursor apply, that's going to stage that memory from the CPU to the GPU. So let's run that and execute the results there. Just play the results. We can see that we have an object, so that's our quadratic input object. And then if we execute that version 3 of our shader and plot the results, there's our good old familiar quadratic curve. So there's some examples of doing some really, really simple operations with SlangPy. There's obviously much more to SlangPy than that, but this should hopefully give you a sort of fairly a high-level view of how you get data from Python into Slang, how you get data from Slang back into Python, and how you would work with it. So the next thing we're going to look at is auto-differentiation. So perhaps spend 5 or 10 minutes playing with what we've seen so far. Pause the video and then come back in 5 or 10 minutes, and then we'll have a look at auto-diff. Thanks for listening so far. See you in part 2. Welcome back. So I hope you managed to have a little play with SlangPy and Slang. What I'd like to look at now is auto-differentiation, or auto-diff. So what is auto-diff? Well, auto-diff is the ability for the Slang compiler to generate a forward and a backward pass. So it allows it to generate derivatives of a function with respect to some input or some output. So why is this important? What do we need it for? It's used fundamentally in things like AI for backpropagation and training, where you would, for example, compute the loss of a particular output with respect to its input. But it's used for many other things as well, particularly in graphics. In fact, increasingly in graphics. So neural rendering is one. Things like computing gradients for neural radiance fields. And Gaussian splatting is a very sort of current topic for these. In fact, there is a fantastic neural shading course that is also part of this series, which I highly recommend that you check out. Differentiable rendering. So this is something where for a renderer that fundamentally outputs a pixel, which is what a renderer's job is doing, a differential render will allow you to compute gradients from the pixel, the final output of the pixel, to everything that actually generated that pixel. And this is great because if you can generate gradients, there's lots of fun things that you can do with them. Physics simulation is another popular use of auto-differentiation. So finite element and inverse kinematics and things like that. Procedural noise generation, and of course AI that we've already talked about. So what is auto-diff exactly? Well, it computes exact derivatives of any function. So it means that you don't have to do it yourself. Whilst computing derivatives of a simple function is not particularly difficult, as functions get more complicated, so do your derivatives. If you need to use derivatives of a function, the chances are you'll be writing a separate version of your function to do that. So if you can get the compiler or the language to do that for you, it means that you've got less chance of making a mistake. You've only got to maintain one version of your functions because Slang just generates it all for you. So forward mode versus backwards mode. We talk in terms of a forward pass and a backwards pass. So a forward mode is when we're getting when we're going from the input to the output direction. So we're getting the derivatives of the output with respect to the input. So this is efficient when there's few inputs and many outputs. So it changes with how the output changes with respect to one input at a time. So you change one input, what does that do to the output, which is basic calculus. Then you've got reverse mode, which is what we are more interested in for the things that we do with AI. And this is the output with respect to the input. And this is where we're saying, okay, we have this output. What made this output this output? And this is efficient when we've got many inputs and only a few outputs. So it's how one output changes with respect to all of the inputs. And this is how we compute, the change in weights with respect to the loss in a neural network. So we're going to look at an example, and this is a very common thing that we would do with auto-differentiation, which is gradient descent. And this, again, is how neural networks change. It's how neural networks train, and there's many other things that we can use gradient descent for. So going back to our Python notebooks, we're going to look at the Slang Auto-diff notebook. So we won't go through how notebooks work again, but we have this Slang Auto-diff Python notebook, and we also have the Slang Intro Auto-diff Slang. Now, I'm going to walk you through this Slang file first of all. It's not dissimilar to the one we had before. It's slightly more complicated. We're doing slightly more. So I'll walk you through the Slang part first, and then we'll look at the SlangPy. So notice that we've got this data point and quadratic params. And we've made these inherit the idifferentiable interface. So just like we saw in Nia's talk, you can make a struct in Slang inherit or implement an interface. This is the idifferentiable interface. Now, this is what makes a particular data type differentiable. It's going to track an output with respect to an input or vice versa. We've also got this compute loss function here. And this compute loss function is a function that we've marked as differentiable, which means that we want to run a backward pass in this particular case on this function. You could also run a forward pass. And what we're going to do here is we are going to track the loss, or track how far away a point is from a target point, which, as we'll see in a moment. We also have this main pass as well, which is what we're going to call our differentiable function from. And notice down here, when we actually initialize our quadratic params here, we don't initialize them just as a straight struct. We actually initialize them as a differentiable pair. And what this is its output with respect to input, or input with respect to output, depending on the direction that you're going. When we call that compute loss function, we're actually calling that as a backward differentiable function. So we're actually calling the backward diff version of that compute loss. We also call compute loss just as a normal function to actually accumulate the loss history, as we'll see in a moment. So going back to the SlangPy auto-diff Python notebook, and again, we have documentation here. So everything that we discuss in this video is also documented here. So as we did before, we're going to import the modules that we need. So import SlangPy, import OS, NumPy, and Matplotlib. We're going to create the device, and we're going to load the module from file, and that is the module that we've just looked at there, the SlangPy intro auto-diff. Little green tick tells us that we're good to go. Now I've got a function that's going to evaluate my quadratic, like we had in the first version. But what's happening here is we're actually going to evaluate a jittered version of that quadratic. And the reason for that is what we're going to do in our gradient descent is we are going to fit a set of polynomial coefficients to a set of randomly generated points. And if we plot that in a moment, and we'll see what that looks like. So here I'm just creating a few arrays on the host side that I can store this data in. There we go. And here I'm going to create some buffers. Now, we're slightly different way of creating buffers here. It's basically just creating a buffer directly on the device and passing data straight into it. That's another way that we can create buffers. So let's plot that. So what we plotted here is a set of randomly generated, sort of jittered points. It's a sort of cloud of points that we want to try and fit a curve to these points. So we've got this compute and plot method. So what this is going to do is it's going to call the test quadratic dispatch, and it's going to evaluate a series of points that is based on a rough guess, a rough estimate of what that curve might actually be. We've then got the run gradient descent function, and that's going to run a series of epochs, a series of steps of the main function that we saw that we saw earlier, which is going to call that compute loss method. So let's just initialize those to create those. Green tick tells us we're good to go, and if we call the compute and plot method, That's going to give us our initial guess there. So the initial guess, now I actually did choose values for that initial guess. I actually choose hard-coded values. I'd rather than using random values. Reason being is I didn't want to randomly choose values that just happen to be the exact curve. So these are values I did choose myself. So our initial guess, well, my initial guess was way, way off. But it was just a guess. So, that's what we expected. So let's run gradient descent with 5 epochs. So we're going to run this kernel here 5 times. And each time we're going to update those coefficients. So let's do that and then plot the results. Okay, so that's better. So that curve has kind of turned around and it's started to fit those points now. So let's run 512 epochs for this and see what happens. And then, as we can see, after 512, which is actually not a lot of epochs, we've actually got a fairly good fit of that curve to those points. Now, what we've also done is, if we look back at this this SlangPy shader here, we've actually called compute loss just as a normal function to actually get the actual loss of that step where we are at that particular point in time. And we've actually stored that into a loss history array, which we can now plot. So if we plot that, you can see that at the very start, after our first few epochs, the loss is very, very high. So our mean squared error loss, our sort of L2 mean, was 2,500. And it very, very quickly drops. So once we're at 300 epochs, we're getting very, very close. And then by the time we're at 512 epochs, it's fairly well stabilized. So this should hopefully give you a good, easy to follow idea as to how gradient descent would work with something like Slang. How easy it is to do auto-differentiation and gradient descent in Slang. This is a methodology you can apply to many, many things, and it's something that you can again implement in just a few lines of code. So I would like to thank everyone for joining us today, and I wish you all the best with your Slang and SlangPy journeyings in the future. Thank you.
Thank you, Chris. Now let's go ahead and close out this lab. We started with language basics, control flow like if and for loops, in-out qualifiers on parameters, types, and so on. Then we showed how to use the lower-level slangc command line to compile shaders of different languages, as well as some of the options it has. Then we covered porting GLSL, which only involves a few changes to your code, shader.io, and how Slang makes things easier, debugging tools, as well as the demo of how Slang worked with RenderDoc, structs, modules, and interfaces, and even a bit of generics. Then Chris covered SlangPy, and finally automatic differentiation. The official Slang docs are at this link below, which have a lot more information about all of the topics that we talked about. There were also many other sessions that occurred at SIGGRAPH that were about Slang. We have our lab materials online, which include the slides, as well as all of the materials that you downloaded during this talk, as well as a landing page for some of the other Slang sessions that happened during SIGGRAPH. If you have access to SIGGRAPH View on Demand, you can watch content from the N-Site Graphics Gaussian splatting sessions, which use Slang as their shading language, as well as the Introduction to Neural Shading course, which largely revolved around Slang. There was also a Kronos Birds of a Feather about the roadmap for Slang and how it will develop in the future. The video recording for that is already online on Kronos' YouTube channel. And then finally, Jose Emilio Munoz Lopez gave another lab on hands-on Vulkan ray tracing with dynamic rendering, showing you how to add ray tracing using Slang to an existing application. The tutorial for that is text-based and is already online as part of the official Kronos Vulkan tutorial. Chris Abert and I both hope you enjoyed this lab. Thank you very much.